Howdy folks, welcome back to Professor Carbon. In this video, what we're going to do is go over an NMR interpretation problem for the molecule shown here, or at least the experimental data shown here. I guess it's our job to come up with the molecule. So as with all of these videos, what I encourage you to do is actually just take a minute, pause the video, and try to work through the problem all on your own before listening to how I arrived at the solution. So I'm going to encourage you to do that right now. Okay, welcome back. Hopefully you at least have a good guess at what this molecule could be. And I'm going to take you through at least how I approach and analyze these problems. So the first thing I'm going to do is point out that we are not given any mass spec data. What we are given instead is the elemental formula. And that's a big benefit because it means we don't have to do any guesswork on what combinations of C's, H's, O's, and N's might be giving us the formula. So with that, I always encourage people to start with the degrees of unsaturation because knowing the number of degrees of unsaturation can give us a couple of clues really early on in case we're missing something. So the way that you always calculate this is you take 2 times the C. And so if I have C9 times 2, I should get to 18. And that's the number of hydrogens you get for any N-alkane. And then, of course, you need 1 hydrogen for the end on both sides. So we're always going to add 2 to that. So plus 2 equals 20 H's in a saturated system. Okay, so 20 is the expected number of hydrogens. What we're going to do then is take 20 minus the number that we have is 8. And so that equals 12 missing H's. And because when you hydrogenate a double bond, right, you add 1 hydrogen to both sides, that means only 1/2 the number of missing hydrogens is our degrees of unsaturation, right? So a double bond is 1 degree of unsaturation. If you saturate it, you add 1 hydrogen to both sides, and so it's 1/2 the number. And so 1/2 of 12 equals 6 degrees of unsaturation. All right, that's important, so I'm just going to box that in right there, and we're going to use that as a point of reference later on in the video. What I like about degrees of unsaturation, again, is it should only take you a minute or two to count it, but hopefully by utilizing it, you'll recognize that something is amiss with your data. And in this particular problem, the thing that we're going to want to notice is that we have an additional ring in the structure, and that should be evident from the degrees of unsaturation. All right, the next thing I encourage people to do is just to scan all of the data and look for the things that are like blinking lights for you to interpret. Okay, so try not to read it from left to right, try not to read it from right to left, and try not to just focus in on one peak and interpret everything you can there. Just scan everything and see what sorts of things are big clues. And at least one big clue pops up right off the bat, and that's this carbon peak, and you'll notice they're listed down below. And so a carbon resonance at 192 must be a CO, and that counts as 1 degree of unsaturation, which is good because we now have 5 more degrees of unsaturation to identify. If we have a carbonyl, we should be able to go in the IR and be able to find that key CO stretch. And indeed, we have that right here. And if we look, this is 15, 16, looks like it's just shy of 1700 based on a quick eyeball. And that in combination with this being below 200 in the carbon NMR tells us that we might have an aldehyde or a ketone, and they're probably an alpha beta unsaturated or conjugated ketone or aldehyde. Now, because it's ambiguous based on this so far, whether it be a ketone or aldehyde, the very next thing I'm going to do is try to go identify whether it be a ketone or an aldehyde, because that helps me know something really important right off the bat. So if I go look, aldehydes and carboxylic acids, remember carboxylic acid should have a broad peak around here, and aldehydes should have a nice sharp peak somewhere around 10. And there's nothing there. Now, anytime you're relying on the absence of a piece of data, I always encourage us to be very careful with that. So that's called interpreting negative evidence, and it's quite dangerous in general. But in this case, we have 8 hydrogens, and we can add up here 2, 4, 6, 7, 8. And we actually have all 8 of those hydrogens visible. And so we can positively assign or state that none of the visible hydrogens have the chemical shift required to be an aldehyde. If it's not an aldehyde, then this carbon must be a ketone. Okay. And that's nice because if we're going to keep track of some fragments, we can right off the bat put something like this as one of our fragments. Now I said that because this number here is below 1715-ish, it's actually below 1700, that's a strong indication it's probably a conjugated ketone. We don't know conjugated to what yet, but that also matches here with the chemical shift below 200. So remember, normal ketones are usually around 210. This one is well below 200, and so that's a pretty good indication it's alpha-beta unsaturated. Looking at what it could be conjugated to, well, we have 1, 2, 3, 4, 5, 6 sp2 carbons, and those are going to be 1, 2, 3, 4, 5, 6, and so that's good. And that matches this bunch of hydrogen signals that we have between 7 and 8 ppm in the hydrogen NMR. Remember, if it's above 7 like that, it's got to be an aromatic system. It can't just be a bunch of random alkenes. So having 6 carbons with about 4 hydrogens in the proton NMR, that's a pretty good indication that we have a benzene ring. And I'm just going to put X on here, and I don't know where the other Y group is, so I'm just going to put Y on there. But I know the benzene has to have 2 groups on it because I have 4 hydrogens in the NMR. So I've got 2 from here, 1 and 1, and so that's 4. Benzene has 6 spots, so if you're missing 2 hydrogens, it's got to be 2 groups. And because it's a conjugated ketone based on both the carbon and the IR stretch, what I'm going to do is just connect those. And so now I have one big piece here, and I still don't know where that Y group is, but at least I know I have this phenyl ketone or acetophenone-like motif, so that's pretty handy. And I'm not really worried too much about the exact splitting or coupling yet. You'll notice I haven't interpreted that. All I did is say I've got 4 hydrogens in the aromatic region, and I have an alpha-beta unsaturated ketone, and so let's just connect those. Looking at the other pieces, now this signal here is going to be coupled to that signal. And they unfortunately don't look like nice triplets like we might expect. But remember, on a benzene ring, there's no way for Y to couple to anything on the benzene ring throughout. So if I have a CH2 unit here, it's never going to be able to talk to that CH2 unit through the benzene system because it's too many bonds, right? It would be 1 bond from hydrogen to carbon, then we'd have 2, 3, 4, it'd be a total of 5 bonds. And so that's typically way too far to see any J value. And so since we only have 2 signals in this aliphatic region, those 2 have to be communicating, and they look roughly about the same pattern. Okay, and so for those of you that haven't heard this before, my kind of zeroth rule of NMR is if I'm coupled to you, then you're coupled to me, and we couple to each other with the same J value, by the same coupling constant. And so that's important because if you see splitting over here and you see splitting over here, then those 2 have to be talking to each other, and they have to be nearby. So since these are both CH2 units based on having the integration of 2, I'm just going to write that down here in blue. So I've got a CH2, and it's got to be next to another CH2. And now I have a box, and I don't know what is on the other side of those boxes. Cool. This is good news because now we have all of our hydrogens accounted for. There was a total of 8 hydrogens in the molecule. 4 of them are on our benzene ring, right? So we have 4 H's on there, and we have our other 4 H's here. And so all of them are taken care of. That's important because it means we don't have any OHs or NHs. And that's true too, because we don't see any big OH stretching in that region of about 3,200. And so that's good that we didn't need to come up with an OH, because it would be nerve-wracking if not being able to see that in the IR. Now the chemical shift pass here 4, that's got to be probably an oxygen. So at least one of these 2 fragments here is going to have to be coupled to an oxygen, and then we'll just extend that out, and at least that'll explain that chemical shift. Now this is where our degrees of unsaturation are going to shine, because it's problematic to try to figure out how to get these things to stick to each other, given that we have 4 openings. Right, we have a Y group on the benzene, we have the other side of the ketone, and we have to put something on both sides of the CH2O chain. Well, the benzene ring itself counts as 4 degrees of unsaturation, right? There's 3 double bonds in a benzene ring, and there's a ring. And so overall, that's 4. The carbonyl counted as 1, and so that gets us up to 5. But we know from our earlier work that we needed to get to 6 degrees of unsaturation. Well, degrees of unsaturation can be from carbonyls, which we don't have any more of because we have all of our carbons assigned, and there's only one in the carbonyl region, and then don't have any other functionality. There's only one IR stretch. So it can't be a carbonyl. It's not going to be a double bond because we don't have anything in the double bond region in the proton NMR, and we've used all 6 of these carbons here in our benzene ring. So we don't have any more double bonds. We don't have any alkynes because that would require 2 degrees of unsaturation. We only have 1. So the last thing that this could be is a ring. Okay, that's the only thing that's left that would give us that degree of unsaturation, is to take the chain and stick it together. And this is great because now I've got, one big opening over here. I've got a second opening over here, and I've got one opening here, and I have to connect something to Y over on that side. And so right off the bat, then I could connect and get one of 2 possible structures. So this would make sense. And the other possibility, just by connecting them in the opposite direction, would be this product. And we can tell apart which of these 2 it is very easily because we know we had to have a ketone. And because of that, this is an ester. So it can't be that. The ester O carbon would be about 170 ppm in the 13C NMR. Maybe a little bit less. This one's conjugated, so maybe 165. But in any event, it's much lower than 192. And so because this shift is at 192, it can't be that ester. And so this then has got to be our product. Now, I always like to go back through and check all the details after I draw a structure and just make sure everything is aligning. And by the way, we should also be able to identify which ones are going where for our hydrogens. So let's just take some time to do that. The carbonyl here we know is at 193, so that's good. The 67 has to be the oxygenated carbon, and 38 has got to be the last remaining carbon, and that makes sense because this thing is next to a ketone, so it's dragged down a little bit, but it's still in the what I call the sp3 land, which is all the things kind of below 45 that are not directly bound to a heteroatom. It turns out that the signal down at 162, which is this one, is pretty indicative of being directly bound to a heteroatom. And so if we think about things in the carbon NMR, remember if we have our generic carbon shift and it becomes oxygenated, there we might say that that's plus 45-ish or so ppm. Well, if we take something here at 120 and we add 45 to it, we get to pretty much the same chemical shift range. And so, by virtue of being directly bound to that oxygen, we see that same dragging down field in the sp2 region, just like we see in the sp3 region. It just has a different starting point. And so those above, probably between about 158 and 165 have a pretty good chance of being directly bound to a carbon heteroatom. And so that's pretty nice. For those of you that are advanced NMR interpreters, you'll also notice that this is a little itty bitty peak. And while I don't have time today to explain why that one's a little itty bitty and the other ones are quite tall, it is something that indicates it's probably a tetrasubstituted carbon atom. In this case, it's the one directly bound to the oxygen. These 4 big ones here are going to be the 4 that are going to contain the CH bonds, and we're not really going to worry about what those are. They're all pretty much in the same range, and so all of these last 4 here are going to, or 5, are going to be kind of in that range here, and I'm just going to box them in, and I'm going to say that they are 135 to 118, and those are the five remaining carbons. Cool, so let's go back to the hydrogen NMR, and let me just change colors here to green. So we have this CH2 is the most upfield. Now you'll notice that that is at about 2.8, so that's pretty high to be next to a ketone, but we'll go with it for the moment because that's really our only option. Usually next to ketones is about 2.2. It turns out in this particular system, because it's beta to that oxygen, it's dragged down just a little bit more, but we'll put it at about 2.8 ppm for those 2 H's, and it's the 2H signal. This signal here, I'm going to eyeball it about 4.5, and that's got to be this one here, 4.5 ppm. And again, that's pulled further downfield than we would normally like it to be, but we can consider a resonance structure here. Excuse me, where that oxygen lone pair on the bottom oxygen is actually delocalizing all the way around up into the carbonyl oxygen. And so that's pretty cool. And because of that, this carbon and the adjacent hydrogens feel as though they're a little bit more positive than they otherwise might be. And that pulls them downfield just a little bit more. Now, interpreting the aromatic hydrogens can be quite challenging. And in here, we can see that this looks kind of like a doublet of doublets. The bigger coupling matches pretty closely to the coupling out here. And so that's, quote, a normal coupling that we might imagine to be about 7.5 hertz. But then it looks kind of bolded. And that bolded is because there's a really fine coupling in there that's bringing it out. And the quote, normal 7.5 hertz coupling is the ortho coupling, and that really fine kind of coupling that's even difficult to see unless you really squint at it is the meta coupling. And because the chemical shift of this resonance is dragged the furthest downfield, that's going to be the one that's going to be ortho to the carbonyl, and that makes sense because it'll have one hydrogen both ortho to and meta to it. And so we can assign that as being the one. I'm going to call it 7.8 ppm. This one looks like kind of a mess, and to me it looks sort of like a weird triplet that is also bolded. And so it's going to have a hydrogen, 2 ortho ones are going to give us the triplet-y shape. So we're going to have one coupling from an ortho and then another coupling from an ortho, and then the whole thing is going to be split. So we're going to need it to be ortho, ortho, and meta to something. And so that's going to be this one here, because it is ortho, ortho, and then meta all the way up there. Okay, so that's going to be at about, let's see here, 7.5-ish. We'll call that one 7.5. And then lastly, we have those that are ortho and para to the oxygen on the bottom, respectively. And because both of those are at positions where that oxygen is donating, because that oxygen serves as an ortho-para director, it's going to be the signals that are going to be the furthest upfield are going to feel that donating effect. And we're not going to be able to interpret the coupling constant because they're overlapping. And so it's going to be kind of a mess. But regardless, that kind of matches all of our data. And so hopefully I've given you now both a flavor of how you can just strategically use degrees of unsaturation to build up pieces that you recognize from key signals, and then how you can kind of put it together. And furthermore, then take some of the actual detailed, super fine nuggets and see if it all checks in that final product. The biggest mistake I think that folks made when approaching this problem was trying to force an aldehyde into their equation instead of another ring. And of course, we know from the lack of these signals really above 9 ppms that there cannot be a carboxylic acid and there cannot be an aldehyde in the structure. And so you very quickly wanted to eliminate either acids or aldehydes and then focus on that last degree of unsaturation as having to be the result of a ring, because it can't be a double bond. There's no regular old double bonds in the system. All right, thank you for tuning in. Hopefully you're finding these videos helpful. Feel free to leave a comment or a like, and of course, feel free to keep watching the Professor Carbon video. Have a great day.